Hi, I'm Junhyeok from KAIST. I'm a PhD student under advice of Professor Myoungsoo Jung. In this talk, I'll present you my recent work, GraphTensor, Comprehensive GNN-Acceleration Framework for Efficient Parallel Processing of Massive Datasets. Before moving on to the main talk, let me briefly summarize the work in a single slide. Graph neural networks, or GNNs, are widely adopted in various large-scale applications such as social network recommendation systems and scientific applications. They are delivering groundbreaking accuracy to graph-based learning tasks, quickly replacing the traditional methods. However, their graph-natured data processing makes a difference between GNNs and existing networks, requiring a new framework for them. We propose GraphTensor, a comprehensive framework that supports efficient parallel neural network processing on large graphs. Our evaluations showed that GraphTensor exhibited 1.4 times better training performance, as well as 2.4 times better end-to-end performance compared to emerging GNN frameworks. Let me start the main talk by introducing our target research domain. GNN's goal is to generate an embedding vector that represents a vertex with multiple numerical values that are useful for the learning task. To this end, GNN gets a graph and feature vectors for all the nodes. Then, for each target node to generate embedding vector, the model first traverses the neighboring nodes that are far from the target node and generate embedding vectors for the nodes one up closer to the target node. The model iterates this process as many as its number of layers and generate the final embedding vector for the target node. Specifically, GNNs perform 3 operations for each layer. The edge weighting weighs each edge by examining the embedding vectors of source and destination node. Then the aggregation accumulates the source's vectors to the destination, reflecting the associated weight. Finally, the combination applies multi-layer perceptron to the accumulated vector and outputs the embedding vector. While the GNN algorithm is inspired by conventional convolutional neural networks, there is a gap between data processing of GNNs and conventional neural networks. In particular, GNN's edge weighting and aggregation require understanding a sparse structure of graph, whereas conventional neural networks such as CNNs and transformers consists of operations on dense tensors. This imposes limitations on the existing deep learning frameworks in terms of both programming ability and processing efficiency for GNNs. Also, GNNs are heavy. This is because even processing of few vertices will require traversing a large region of graph nearby the target node. Further, the input graph for GNN is often large, accounting hundreds of gigabytes, which makes it hard to be loaded into GPU memory. Recently, there were several approaches that address these issues. First, deep learning leveraging approach leverages existing deep learning operations to implement aggregation and edge weighting. For example, when they perform edge weighting, they first convert sparse information of graph feature vectors to dense matrices. This sparse to dense conversion makes existing operations available for processing the data. Therefore, this approach leverages existing operations such as element-wise multiplication to generate the edge weight, enjoying the massive parallelism of GPUs. However, this sparse to dense data conversion generates a redundant embedding in the GPU, wasting GPU memory. We found that it increases the memory footprint by 5.8 times, even generating out-of-memory error for a large graph. To address this issue, the graph simulation approach introduced operations that works with both graph and embeddings. Specifically, they treat the graph as a sparse matrix and employ sparse matrix algebra such as SPMM and STDMM to simulate graph processing. These operations are processed in GPU using edge-wise stretch scheduling, which is from traditional graph processing. This scheduling is optimized for processing many edges in parallel. The edge-wide thread scheduling allocates a thread block per edge to process multiple features in the associated embeddings in parallel. However, such a scheduling makes different edges with the same destination processed by different SMs, placing multiple copies of destination embeddings across different SMs. This cache bloat issue needlessly loads 81% more data to the cache, making their cache management less efficient and increasing the global memory accesses. Lastly, to narrow the region for graph traverse and process large graph using GPU, existing frameworks employs GNN Preprocessing. Specifically, it first reduces the number of vertices to compute by sampling the neighbors. Then it retrieves necessary region near the target node from the entire input graph. This is done by reindexing the graph, looking up the sample nodes from the original table. Lastly, it transfers the retrieved graph and embeddings to the GPU. While this pre-processing is vital for GNN-Acceleration, it is a time-consuming task. We found that this pre-processing accounts 84% of the total training time on average. Next, I'll introduce our solution that addresses all the aforementioned issues. We propose GraphTensor, a comprehensive GNN framework that supports efficient parallelization for entire GNN processing procedures on a large graph. Our solution consists of front-end and back-end. The front-end offers GNN-specific programming interface, providing destination-centric GNN primitives that eliminate the memory and cache bloat. The back-end service-wide tensor scheduler reduces the end-to-end latency by introducing pipeline parallelism to the pre-processing. In addition, the kernel orchestrator optimizes data flow graph of GNN for further acceleration. To eliminate memory and cache bloat, GraphTensor traverses the graph in a destination-centric manner. Specifically, GraphTensor groups all the nodes associated with each destination node and allocates them to be processed within the same SM. In addition, since GNN needs to process features with much higher dimension than traditional graph processing, we also partition the feature vectors and allocate them across multiple SMs. Since this thread scheduling eliminates the redundancy of embeddings from GPU's memory and cache, it can remove memory and cache bloat issue and improve the performance. Our kernel orchestrator further accelerates the GNN processing latency by reducing the embedding dimensionality. Specifically, it exploits the aggregation and combination reduces the embedding table's dimension differently. Since aggregation accumulates the sources vectors for each destination, it reduces the number of rows from the number of sources to the number of destination. In contrast, combination transforms each vectors, reducing the number of columns from the number of original features to the number of hidden dimension. Because of these characteristics, the size of the input tensor for following operation varies significantly based on which function is applied first. Since the size of the input tensor determines the execution time, we can minimize the execution time by exploiting this behavior. While the default execution always executes the aggregation first, our dynamic kernel placement rearranges the aggregation and combination kernels if the combination can reduce the total amount of input tensors more than aggregation. To this end, our kernel orchestrator checks the data flow graph at runtime and compares the dimensionality of two possible execution order. While these methods shortens the computing latency, the users still experience low performance because of the long pre-processing latency. Unfortunately, it is non-trivial to make individual tasks latency shorter. However, different tasks are bounded by different aspects of the system, such as memory and PCI interconnect. Thus, service-wide tensor scheduler parallelizes the pre-processing tasks, utilizing different system resources simultaneously. Specifically, it first splits the pre-processing tasks into multiple per-layer subtasks, which relaxes the dependency between the tasks. The subtasks are then scheduled in parallel while being aware of dependency between each subtasks. For example, reindexing, lookup, and transfer can only be performed after each per-layer sampled graphs are ready. Considering this, we first schedule sampling subtasks back to back. Further, size of the GPU memory spaces for the graph and the embedding table are determined after all the sampling subtasks are done. Thus, the scheduler sets a barrier before running transfer that waits for sampling's completion. The remaining subtasks are also scheduled considering their dependency. Lastly, let me introduce the evaluation result of GraphTensor. For the evaluation, we implement GraphTensor A-top TensorFlow and tested it on a system employing RTX 3090 GPU. We tested multiple variants of GraphTensor, accumulatively applying each of our ideas, and compared them with popular GNN frameworks and recent prior works. Compared to popular GNN frameworks DGNN PyG, our destination-centric GNN computing showed 1.4 times better performance by eliminating memory and cache bloat. Dynamic kernel placement further improves the performance by 41% since it rearranges the data flow graph to follow better execution order. We also compared the prior work GNN Advisor, which optimizes workload balance across SM cores but leverages deep learning operations for edge weighting. GraphTensor showed 2.0 times better performance than GNN Advisor. From the end-to-end perspective, our service-wide tensor scheduler reduced the end-to-end latency by 2.7 times on average. This is because it parallelizes the pre-processing by relaxing the dependency chain with smaller subtasks. Our GraphTensor also exhibited 1.7 times better performance than the prior work Salient, which overlaps the pre-processing latency with training latency without parallelizing the pre-processing. As a conclusion, we proposed GraphTensor, which support efficient parallel neural network processing on large graphs. Our work consists of three main contributions. First, we introduced destination-centric GNN computing, which can eliminate the memory and cache bloat. Second, we dynamically rearranged kernels in a data flow graph to employ better execution order by examining the dimensionality. Lastly, we relaxed the dependency of pre-processing tasks and composed parallel execution chain to reduce the end-to-end latency. Thank you very much for your attention.